Hello everyone. In this video, I will explain the physics of the projectile experiment and extract lessons. If we apply them to social scenario, we can navigate challenges more effectively and optimize our path to success. So let's start by answering this question. If your goal is to maximize the distance the ball travels, would it be more effective to throw it straight or at an upward angle? Keep in mind the force in both cases is the same. When I ask my freshman students this question, 40% of the students think the ball will travel further if I throw it straight forward. The reasoning is that all my force will be pushing the ball to travel straight forward, and the ball will be traveling faster and further. The math supports this reasoning because velocity equals momentum divided by the mass of the ball or the rock. Now momentum is force multiplied by delta t. Delta t is the time it takes me to apply my force to the ball to push it. So it's the time until I let it go. While if I throw the ball upward with some angle, now my force will be divided between pushing the ball horizontally, and part of this force will be gone to push the ball upward. And the velocity will be v cosine theta, so less than this velocity. Well, in this video, we will answer this question by carrying out the experiment and also do theoretical analysis. In the experiment, we will be using the following tools. We have a launcher here, and we have a steel ball of mass 0.017 kilogram or 17 gram, and we will be inserting the ball here, and inside this launcher there is a spring. When we pull this string to trigger the ball to come out, the spring here will exert a force equal 0.94 Newton, and the time it takes the spring to push the ball out, delta t, will be 0.1 second. So if I calculate the velocity, the ball will come out. It will be the force 0.94 multiplied by delta t 0.1 divided by the mass 0.017 kilogram. So that will be 5.53 meter per second. Now this launcher, we will mount it on this table, and the launcher is 1 meter above ground. So h is 1 meter. So this will be the launcher, and when I want the ball to travel path A straight forward, I will mount the launcher this way, so that will be 0 degree. Theta here is 0. When I want the ball to go path B upward with angle theta, then I will mount the launcher this way, and I will be reading the angle here. Okay, let's first carry out the experiment to determine which path will allow the ball to travel further and collect data. After that, we will do theoretical analysis. Hopefully, the experimental data will agree with the theoretical analysis. This is the setting of the experiment. The launcher will throw the ball, and it will fall on the black carbon sheet, and this will mark the location on the white sheet. The first experiment, we set the angle theta of the launcher to 0, so it will shoot the ball horizontally. Okay, the ball fall at 2.5 meters, 250 centimeters. The second trial, we set the angle of the launcher to 10 degrees, so it will shoot the ball a little bit upward. it seems the ball traveled further with increasing the angle from 0 to 10 degree. It traveled more than 310 centimeter. I carried out the same procedure for angle 20 degree, 30, 40, 50, 60, and 70 degree. And the distance traveled horizontally kept increasing up to the angle 40. After that, it decreased again. And the results are as follows. This is the data for the experiment, where theta 0, it traveled 250 centimeter or 2.5 meter. That's this case, theta is 0. And as we increase theta to 10, 20, the ball actually traveled further, 312.5 centimeter, at 20, 359, and so forth. So it just keep increasing until the angle is around 40. That's the maximum it can travel, 395 centimeter, which is 3.95 meter. If we increase theta further to 50, then the travel distance is less and less. At angle 70, it traveled 243 centimeter. It's even less than when the angle is 0. Let's carry out the theoretical analysis to verify this data, what we collected from the experiment. And also from the theoretical analysis, we may find an answer why at this angle, 40 or around 40, the distance is the longest, the ball to travel. So the general case, basically, theta can have any value, 0, 10, 20, 30, 40, and the goal is to find the distance traveled by the ball for a different value of theta, where v0 will be constant. That is the velocity due to the spring pushing the ball with a certain force equal 0.94, and the mass of the ball is 0.017 kilogram. In path B, the force will push the ball in this direction. Part of the force will push the ball to travel horizontally, and part of the force will push the ball to travel vertically. So the velocity is still the same because the spring is still exerting the same force, the same mass, the same delta t. So this v0, the ball will come out of the launcher with a speed 5.53 meter per second. But part of this velocity will allow the ball to travel in the horizontal direction and with the speed v0 cosine theta. And part of this velocity will allow the ball to travel upward with the speed v0 sine theta. Now the distance it will travel, it equals this velocity, v0 cosine theta, multiplied by time. So that's v0 cosine theta multiplied by time. Now the challenge is to find t. How long this ball will stay in air before it collides with ground. So to find t, we have to do vertical analysis. So the total time the ball will be in the air equal t1, the time it takes the ball to travel upward, plus t2, the time it takes the ball to fall down to ground. So this t will be t1 plus t2. So let's find first t1 by doing motion analysis for this part. Basically, how long it will take the ball to travel from here until it reach y1. We will be using this motion equation, which basically says the velocity in the vertical axis, Vy, in this vertical axis at any instant of time, equal the initial velocity of the ball in the vertical axis, plus the acceleration multiplied by time, which is this one, t1, how long it will take to reach that maximum amplitude. Well, the velocity when the ball at the maximum amplitude will be 0. Just imagine it will travel upward until it reaches the maximum distance. Then it will stop, then it will start falling. So at that instant of time, the velocity Vy will be 0. Now the initial velocity for the ball to travel upward is this one. It's the component of V0 along the vertical axis, V0 sine theta. So v0y then is v0 sine theta. Plus acceleration. The only force acting on the ball when it's traveling upward is gravity. And the gravity is pulling it downward, the opposite direction of the travel, with acceleration minus g. Multiply by the time, t1. t1 is the time to reach the maximum distance upward. So if I solve for t1, t1 will be just this one divided by g. So v0 sine theta divided by g. Okay, so I found t1. Now I need to find t2. Well, to find t2, let's first find the distance for the ball to travel from the top height all the way to ground. Well, y2 consists of two parts. First, it's the distance from ground to here. So that's h. So y2 is h plus this distance. And this distance is y1 plus y1. Now, y1, we can find it as follow. Well, the distance here, if the ball is traveling upward with a constant acceleration, which is in this case the gravity, then the motion equation is the following. The distance equals the average velocity between the initial velocity and the final velocity multiplied by t1. The time takes the ball to travel upward. Well, the initial velocity is v0y. So that's v0y is this one. The final velocity, we said when the ball reaches the maximum height, it will stop, then come down. So at that instant of time, the velocity will be 0. So vy will be 0. Divided by 2, so this is the average velocity for the ball traveling upward, multiplied by t1. And t1, we just found it here. So then it is the average velocity here, multiplied by this quantity, and y1 will be this value. Okay, so we found y1, and we said h is already given 1 meter, so y2, all this distance is h plus y1. So that will be h here, and y1 we just found it to be this quantity. So if I add h plus this quantity, I will unite the denominator to make it 2g. So that's 2g times h is this one, plus this quantity here. Okay, so I found y2. Now I need to find t2. And after I find t2, I know how long the ball stayed in the air with this projectile. It's t1 plus t2. So let's see how do we find t2. Well, I will be using this motion equation, which basically says the distance traveled equal the initial velocity multiplied by time plus half the acceleration of the object multiplied by the time square. So the distance for the ball to fall from the highest amplitude to the ground is y2. So this distance is y2. The initial velocity, as I said before, if the ball is here, it stopped, then it starts coming down. So the initial velocity is 0. So that's 0 plus half. The acceleration is gravity, and the ball is traveling this way, and gravity is working in this direction. So that's plus times the gravity multiplied by t2 square. And y2, we found it in the previous slide, equal this. So now if I plug for y2, this quantity, that will be this one, equal half gt square. Again, a reminder, what I am after, I want to find the time the ball in the air. That would be t1 plus t2. We already found t1 in previous slide, which is this. So now I need to find t2. Well, now I have this equation, so I'm going to solve for t2. So t2 will be, 2 will cancel this 2. The g will come here, g square, and they take square root of this to get t2 here. So the total time the ball will be in the air is t1 plus t2, t1 plus t2. And t1 will be v0 sine theta over g, so that's this component, plus t2, which is this component. And this is the total time. Now I can calculate this distance x. So x here will be v0x, which is the horizontal velocity, v0 cosine theta, multiplied by t, which is this quantity. and that's the distance. So the distance depends on the following. First, V0. It also depends on theta. V0 is fixed because it depends on the force of the spring, so it doesn't matter if the launcher has an angle of theta or the launcher has an angle of 0. V0 will be the same. All right, so let's recopy these to the next slide. So now this is the horizontal distance traveled by the ball in the general case or in the special case. So the distance traveled is the velocity in the horizontal direction multiplied by time. So now if I want to find the distance when theta equals 0, all I have to do is plug for theta 0. So then x here will be now cosine 0 is 1. This will equal 1. Sine 0 will equal 0. And this quantity will equal 0. So then we have it V0 and this is the distance traveled horizontally if theta is 0. It will be V0, the velocity coming out from the launcher, square root of 2h. h is the distance, g is the gravity. So if I plug value, V0 is, we calculated earlier, is 5.53 meter per second, and the time here, 0.45 seconds. You multiply them, you get the distance 2.49 meter or 249 centimeter. So in this case, it will be traveling 249 centimeter. So let's plot this equation. So I'll be changing theta from 0 until 90 degree and find x. And I will plot x, the distance traveled versus the degree of the launcher. So when I plot this is the curve I get. The x-axis is the angle from 0 degree all the way to 90 degree, and the vertical axis represents distance x. The ball traveled in the horizontal direction. So when theta is 0, the distance traveled is around 2.5 meters or 250 centimeters. As the angle theta increase to 10, the distance traveled even more. When the angle 20, the distance traveled 3.5. As theta increase from 0 to 40, the distance traveled in the horizontal direction increase all the way almost to 4. Then when theta get larger than 40, then the distance traveled gets smaller and smaller. So let's look at this table. This is the value of theta from 0 to 70 degree. This is the data collected in the experiment for x. And this is the data from theoretical analysis for x. Very close the values. At theta equals 0, the horizontal distance, that's this case, traveled is experimentally, we measured it 250 centimeter. Theoretically, it's 249.7. So the difference between them is less than 1%. It's like 0.12%. If you look at this, it looks very, very close. The experimental data and the theoretical data. From this curve, the maximum distance traveled, it's 399.3 centimeter at an angle of 38 degree. So now let's try to figure out why at angle 38 degree, the ball traveled the biggest distance, 399.3 centimeter, which is around here. So what we will do, we're going to plot these, the velocity versus theta, and we're going to plot time versus theta, and also plot x versus theta. So these three plots represent the following. The blue one here is the horizontal velocity of the ball. So I'm plotting it against theta. So this is theta, and this is the velocity curve. The red one here represents time. So I'm plotting this term versus theta. and that will be this curve, which represents the time the ball in the air. And this time this, when you multiply this curve times this curve, you get the distance traveled, which is x here. Now, at angle theta equals 0, that will be this scenario. So the velocity is the maximum. It's 5.53 meters per second, because when theta is 0, all the force of the spring is dedicated to push the ball to travel horizontally. But at theta equals 0, the time the ball in the air is only 0.45 seconds, because now the gravity pull it down. So the ball stay in the air traveling only 0.45 seconds. So when I multiply this times this, I will get this value. So the ball will travel 2.497 meters. As I increase theta from 0 to 10 to 20, now the horizontal velocity will get less, because portion of the force will be dedicated to push the ball up and less forces to push it straight. So the horizontal velocity gets smaller and smaller. But the time where the ball stay in the air get bigger and bigger. Why? Because at this angle, part of the force is pushing the ball upward to reduce the impact of gravity. So the ball will have more time to travel in the horizontal direction. The maximum distance, we said it's around here, when the angle is 38 degrees. At this angle, the velocity is reduced from 5.53 meters per second to 4.3. So the ball lost 20.2% of its horizontal velocity, because less force is pushing it this way, and some of the force pushing it up. But it will stay in air traveling 0.91 second. So that's an increase from 0.45 to 0.91 second. That's 103% increase. And here only 21% decrease in velocity, but it gained more time. So when you multiply this times this, that's the distance it traveled in the horizontal direction. When the angle exceeds 38 degrees, the velocity decreases at a faster rate compared to the increases in the travel time, resulting in a product of velocity and time that yields a distance smaller than 3.98 meters. So basically, at angle theta 38 degrees, the projectile gave up 20.2% of its force to push the ball upward to minimize the impact of gravity. So the ball will have 103% more time in the air to travel horizontally to a further distance. In another word, giving up part of the horizontal force for vertical force makes the ball travel at a lower speed, but it will have more time to travel further distance. For the sake of simplicity, this experiment omitted the consideration of unpredictable wind and air friction forces, which might have affected the ball's trajectory differently depending on their direction relative to its motion. If the wind in the same direction as the ball motion, it will help it to travel further. If the wind is in the opposite direction, it will travel less distance. From this experiment, several social lessons emerge. First, optimal path. Sometimes the most direct route to a goal is not necessarily the most effective. It's crucial to take time to plan and consider all relevant forces that could influence progress toward the goal. 2. Resource allocation. Similar to how we redirected some force upward to extend the ball's flight time, in life, allocating resources to mitigate the impact of unavoidable force can be beneficial. Though reallocating resources might initially appear wasteful, it can ultimately provide more time or resources to achieve greater success. Third lesson, unpredictable forces. Life is filled with unpredictable forces, such as wind, which can either aid or hinder the ball's travel. Plan to maximize gain from such unpredictable factors in our life. 4. Celebrating achievement. It is essential to take pride in one's achievement, regardless of whether they meet initial expectations. Comparison with others should be avoided, as each individual faces unique circumstances and encounter various external forces, such as country of origin, family, and social environment. By applying these lessons from the projectile experiment to real-life scenario, individuals can navigate challenges more effectively and optimize their path to success. Thank you for watching, and I hope you enjoyed it.